So we will now establish a proof which is based on the invariants of this algorithm. What we want to claim is the algorithm discovers shortest paths for every pair of vertices and it discovers them in, I will just write increasing order, but understand that this is non-decreasing order. I mean, there may be paths of the same weight, so it can increasing order of weight. Okay, so let me prove it in the following way. So suppose during the course of the algorithm, whenever we discover a shortest path, we will put it into a set what we will call as opt, right? So in fact, as you see that the first edge we must put it into opt, right? And we will say that suppose the algorithm has built this set opt, right? At some point during the execution of the algorithm, we have built this set opt, and this set opt contains the shortest paths between whatever pairs at the endpoints it is, and the current path at the top of the heap h is p, some path p, right? It will have some weight, right? It will have some weight, and what we want to claim is that 1 p is an optimal path for pair. So I will just say that p is from x to y. It could be a single edge or it could be a non-trivial path for the pair xy. This is my claim. 2. Let's say that the weight of the path, this p that is at the top of the heap, is something. So let's say it is 100. The weight of the path is 100, right? So my claim is that in the graph, all the pairs, say AB, for whom the shortest path distance is strictly less than 100, have been already discovered and put into opt. This is my claim, right? So for all pairs in G such that the shortest path distance is less than weight of P have been discovered and added to opt. And finally, I want to claim something more. So there are also pairs for which the shortest path distance in the graph is greater than 100, right? Actual shortest path may be larger than 100. Then what do you think does the heap contain? The heap may, so let's say that there is a pair A to B for which the shortest path is 150 in the graph, right? We do not know this, but let's say somebody tells us that the shortest path is 150, right? Then what would you expect the heap to contain as an estimate of the shortest path? So suppose there were an edge from A to B, right? And the edge had weight, say some 300, right? Then clearly the weight, the estimate for the shortest path in that PXY array, can it be more than 300? No, because the first time you would have initialized with 300, if at all you would have done any update, you would have only improved this estimate and made it shorter, right? So then it says that for every pair AB for whom the shortest path distance in the graph is strictly greater than the weight of the P, the estimate is min of the weight of the edge AB and something else. Can you say something about this? So remember that we are at an intermediate stage in the algorithm. We have possibly discovered shortest paths. So let us say that there are paths from A to B in the graph which are of the form A, A1 up to B, A, A2 up to B, and so on, right? These need not be shortest paths, there are paths in the graph, right? Let us say that A1 has been discovered and A1B also has been discovered, right? Then what can you say about okay, so what can you say about the estimate? Yeah, so if these paths lie in opt A1 and A1 to B, then these must have been combined during the course of the algorithm. Remember that our step is that whenever you discover an optimal edge, whenever you discover this as an optimal edge, you would combine it with longer paths and create a path which is larger, and therefore the estimate is min of the weight AB and over all min over all, let us say A1, such that A1 to B is a path in G and A1 belongs to opt and A1B belongs to opt, right? If A1 belongs to opt and A1B belongs to opt, we must have merged them and created a longer path. So our estimate would be the min of all these things, right? Because we started with an initial estimate of the edge weight. Whenever we found any paths, we concatenated two paths and then we also created larger paths, right? So this is the claim that we have, that for all pairs in G such that the shortest path distance is greater than the weight of P, we have the estimate as this. And we want to show that these invariants are maintained throughout the course of the algorithm. See, I am not claiming that this is what I have proved, I am just stating the invariants, right? So if I have discovered some paths in opt, I am claiming that I must have combined them and made the estimate only better, and therefore the estimate should be the min of all these things, right? I may not have still discovered the shortest path between the pair A to B if its weight is larger than the weight of the path which is currently at the top of the heap. Are the invariants clear in the statement? We have not proved them. Okay, so let us ask, are the invariants true at the beginning of the algorithm? That is, just when you have initialized the heap. So what is it saying? That P is an optimal path for the pair xy. That is clear because we said that the smallest edge is going to be a shortest path. For all pairs in G such that the shortest path distance is strictly smaller than that, there are no such pairs for which the shortest path distance can be strictly smaller than the weight of the smallest edge. So this is trivially true, and since opt is empty to begin with, nothing has been put into opt, therefore for every other pair the estimate is clearly the min of weight and nothing else, which is actually the weight of that edge AB, and we will say that the weight of the edge AB is infinity if there is no edge between that pair, right? So all the three invariants are true when we begin our algorithm, right? So we want to claim that as our algorithm progresses, these invariants are maintained. Any questions? I see a few blank faces, so I am a little concerned. So if there is any question, please ask me. So sure. So what it says is, okay, so let us just revisit the algorithm. So at some point I am just halting the algorithm and saying that at this point P is the path at the top of the heap, right? So let us say P is the path at the top of the heap. I want to claim that P is optimal, which is a strong statement. This is what I would like to prove, right? And then what I am saying is, if there are pairs for which the distance is strictly smaller than P, then they have been discovered and put into opt, right? But there can be pairs for which the distance is strictly larger than the weight of P. The shortest path distance could be strictly larger than the weight of P, right? So as I said, as an example, P has weight 100. There could be a pair AB for which the shortest path distance from A to B in G is 150, right? I am not claiming that I need to have already discovered that. I am claiming that for all such okay, so one is that certainly the estimate for AB has to be at least has to be at most the weight of the edge AB, because I have initialized it with the weight of the edge AB. Now whenever I discover a path, suppose there are paths of this form, A to A1, the paths of the structure of this form, these are not necessarily shortest paths, A to A1, A1 to B, then A to A2, A2 to B and so on in the graph, and suppose these are optimal paths, then I am claiming that, so okay, maybe the distance is slightly confusing, let me take a distance of slightly larger, say 400, right, and yeah, so this is 100, so yeah, so let us say that this path is of weight 150, this path is of weight some 150 and or even 160, and let us say that the current path that I have on my heap is some 200, right, the top path on the heap is 200, right. So is the example clear? I have a pair AB for which the shortest path distance in G is 320, right. This we have to discover, but somebody told us, let us say the current path on the top of the heap has weight 200. Then my claim is that these paths of the weight 150 and 150 have already been, yeah, I just need to change this a little bit, sorry. So this has become 150 again, so this has become 300, then I need to make it just 290, right. So sorry, again I am changing the example, but this has weight which is 290 and this may not have been discovered, but let us say that I have discovered the shortest path from A to A1 which is 150, I have also discovered A1 to B which is 150 again, then I must have made the estimate to 300, and this edge weight, what did I say? The edge weight again I will make it 500, right. So my initial estimate was 500, I started with an initial estimate of 500. During the course of the algorithm, I must have discovered this 150 and 150, and I must have combined these paths and made the estimate to 300, and I still have not discovered the shortest path, but the estimate that I have when I am seeing this as on the top of the heap is the best amongst all the estimates that I get, right. So if I had something which is slightly better than 300, but maybe still larger than 290, that is 295, I will have the better estimate in that PXY. That is my claim. Is this clear?
So when I saw I wrote 500.
No, that first is completely different. That first is a vertex, remember. It is not a weight, it is a vertex. So it just says that if you are looking at a path from X to Y, then what is the first vertex on that path? It has nothing to do with the weight, it is just to discover the shortest, actually reconstruct the shortest path. So, but you are right that it is exactly equal to the weight that I initialized, right. And please distinguish between the weight, which is the weight on the edge, the distance which is, so this is DAB, this is equal to weight of the edge AB. So when I draw these wiggly arrows, it means that it is a path. When I draw this direct edge, it means that it is an edge. Got it? So this is what are the invariants we want to argue. We are just stated the invariants, right, and we have argued that they are true when the algorithm has just started, that is when you have initialized everything, the invariants are true, right. So now we want to claim that the invariants remain true even at any point during the course of the algorithm, right. So let us say that I actually have some path P which is at the top of the heap, and for the sake of contradiction, it is not an optimal path. This is what I would like to refute, right. So let us say that it is a path which has come to the top of the heap, but it is not the optimal path between that pair xy, right. So what should have been the case? So it is some path that has come to the top of the heap, but the optimal path must have a weight strictly smaller than the weight of this path. right? So P is the path that has come to the top of the heap, and let's call the optimal path as P star, and weight of P star must be strictly smaller than weight of P, right? And furthermore, we will make one small assumption, that remember that the algorithm is progressing, and there must be, if the algorithm is erroneous, there must be a first place the algorithm makes an error, right? So that is, so you keep on extracting paths from the heap. There is some oracle or some god, you can think of it, is telling you that okay, this extraction was correct, till now you are okay, you are with the correct answers, that the optimal shortest paths has been there. Nobody tells you that, but let's assume that there is somebody. Then if there must be a first extraction or first place where you made a mistake, right? And we will hinge our argument on the first place. So typically lot of proofs also follow this argument, where you say that the first place where you make a mistake can never happen, and therefore there can never be the first place, which means that your algorithm cannot make a mistake, right? So we will assume that so what does this give us? That all paths that were extracted before this must have been correct, because of the fact that this is the first mistake that our algorithm did, right? And can it be that the mistake happens on the very first extraction? Not. It cannot happen on the very first extraction, because the very first extraction should have been of the shortest edge, and that is a correct edge that we have identified as a shortest path, right? So maybe we did the third extraction, fourth extraction, and that the seventh extraction we made a mistake, but 1, 2, 3, 4, 5, 6 have been correct extractions. So let us say that this is the first extraction, which is an erroneous extraction, that is, this P doesn't represent a shortest path. Okay, so how does P star look like? I mean, does it, okay, so let us ask, the optimal path must have weight which is strictly smaller than the weight of P, but let us ask in terms of the structure of the path, can it contain a single edge? So can this path between x and y, this optimal path, can it be a single edge from x to y? Yeah, because then our algorithm cannot make an error, because we ourselves put the edge xy into the heap, and if at all we did anything, although I did not write the update algorithm, it only refines or improves the estimate. So if the optimal edge was optimal path from x to y was indeed a single edge, our algorithm could not have made an error, right? So our algorithm made an error means that the optimal path from x to y must look like a long path in terms of the number of edges, right? It better contain at least 2 edges, because those are the paths our algorithm generates, and our algorithm maybe doesn't generate all paths. That is our possible risk, right? So let us look at the first edge. So the path must have 2 edges, at least 2 edges, and the path looks like xa and ay, right? So let us look at the weight of xa and the weight of ay, right? Okay, what can you say about these weights? These are strictly smaller than the weight of the path P star. Is this correct? Because of the, not necessarily strictly smaller, because there can be 0 weight edges, but they are no larger, right? But let's assume also there are no 0 weight edges, just to make this proof simple. So therefore each of these paths individually are strictly smaller, right? So now let us say that, so now the argument is very interesting. So let us see that there is a weight of, okay, so I should write this weight of the edge xa. Remember that because this is an optimal path, therefore this weight of the edge xa is exactly equal to the distance of the shortest path from x to a, because this is an optimal path, right? So this weight of xa is equal to d of xa, and there is also a weight of, not weight, I should write d of ay, right? And remember that both of these are optimal paths, and this is the first time our algorithm has made a mistake for this path P. So all smaller paths were correctly discovered by our algorithm, right? So let us ask, which one of these has been discovered first? We do not know. That depends on the relative weights of dxa and day, right? So there are two cases, there are exactly two cases, assuming that there are no zero weight edges that can be handled, but let's not deal with it. So dxa is strictly smaller than day. I mean, again, they can be equal, but let's think about it, they being one smaller than the other, or dxa is strictly greater than day, right? So let us say that dxa is strictly smaller than day, then dxa will get discovered before day during the course of the algorithm, because our heap processes paths in the order of their weights, right? So what happens when you go to dxa, I mean whenever you discover this optimal edge, actually at that point this day path need not have been discovered and you may not have the estimate. So you would not have combined these two paths necessarily at that point, and therefore you need not have generated this path. But let us look at what happens when day was discovered during the course of the algorithm. So when you discovered day, you must have gone into this part of the algorithm, and at that point you must have known that the edge xa belongs to ea star, right? Therefore you must have combined this the xa to y thing to get a larger path which is xay and obtained this estimate, right? So what I am claiming is you have only these two conditions, dxa is the distance between from x to a is smaller than the distance from a to y, or it is larger. What I am claiming is when the larger of these two gets extracted from the heap, the smaller of the two must already have been discovered, and therefore irrespective of which way it gets discovered, you will certainly have the case that you would have combined this on the larger extraction. That is, if day was the one which got extracted later, at that point xa should have been in ea star and therefore you must have combined it. If not, you must be in the case where xa got discovered later, but then you see that for whenever you discover xa, you have already taken all the w's and actually updated the distances, in which case again you must have combined these two paths xa plus ay and generated this big path, right? So again I will re-emphasize that what I am saying is that if you look at any path that was not discovered by our algorithm, call that as p star, and that was a path which was not discovered by our algorithm, but that was the first such error that our algorithm made. So therefore all other paths which were strictly smaller than it must have been necessarily discovered by the algorithm, right? In particular, if you break the path into the first edge and the remaining thing, those must have been discovered by the algorithm, and we don't know how they were discovered. Maybe xa was discovered first and ay was discovered later, or the other way. But in either case, my claim is that I am going to always combine these paths on the later extraction and generate the bigger path, in which case I could not have missed generating this optimal path which is p star. Sure. So let us, the question is, can we write the exact code for update? Okay. Okay, sure. I will just write down, I will just state exactly. Remember that how is update called? I mean, it is called with 3 vertices, UVW each time, here UVW or TUV. Note that it is always called with an edge which is UV and something which is W. I mean, we do not know, this is just a vertex, right, W, or this TU which is an optimal edge and some V, right. Again, this could be a path, it does not matter, it is called with just a vertex V. But the first pair of vertices which are given form an edge in the graph, that is clear, right, the way we are calling. So we will just write this update. So update UVW. So let us ask, what do you think update UVW is doing? UW part. So, but when should it update the path? Which path is lesser? Which path is a better estimate? Correct. So it just checks if P of u v dot weight plus P of v w dot weight is strictly smaller than P of u w dot weight, then P of u w dot weight is equal to P of u v dot weight plus P of v w dot weight. P of first is equal to v, P of x y dot heap pointer is equal to the heap pointer, right? This is actually the place where you will call a decrease key, that is this thing which is the update into the heap.
So then on the first edge it finds, they don't need to make the path. So for example, find the first smaller edge.
So where are you? Okay, so you agree what is update, right? Huh, good, okay.
When it finds the first smaller edge, for example, it finds UV, which is the smallest edge in that path, which is shown in the example. It finds XA, for example.
Okay.
So then only it will join it with AY now.
But remember that, okay, so in which case are you dxa is less than day or which case?
XA is less than DAY.
Okay, so remember that if when you discover dxa, I mean the edge dxa, the heap is processing paths in the increasing order, right? So therefore at that point would you have discovered ay, the shortest path from a to y? You may have some estimate from a to y. You need not have the shortest path. Therefore, you will combine it with y, but that need not lead to the path dxay, which is the shortest path, which is p star.
When it's an edge, when AY is an edge, then it will lead to the shortest path.
When ay, if ay is an optimal edge, right? Else, if ay, I mean whenever you discover the larger of the two paths, however you have broken it, you are guaranteed that the smaller of the two paths is already has been discovered and put into the appropriate data structure. Therefore, you will certainly join the two paths and combine and get a longer path, right? So the main key takeaway from this is that if you take a path which is the shortest path, you can divide it at the first edge and look at the first edge and the remaining part of the path. Without loss of generality, one of them has to be strictly smaller than the other, right? Of course, you can argue that okay, both of them are 15 and 15, then I will use a tie breaking scheme based on the endpoints of those. So you will always be able to say that one of them is strictly smaller than the other. Do not worry about that case. So one of them is strictly smaller than the other. Then when the larger part of the path gets discovered, the smaller part of the path must have been discovered by the algorithm, and at that point you will certainly join that path and create the longer path. And that I have shown, again I will reiterate. So whenever we if day was the one which was discovered later of the two, then we must have been in this case where this xa edge was already discovered as an optimal edge and therefore was put into the correct data structure, that is EA star, and therefore you must have discovered that. Finally, if this day was discovered, dxa was discovered later, then at that point anyway you would have gone over all the vertices w, and therefore you must have discovered that path, right? So in fact I have not argued that all the three invariants are maintained in the interest of time, but you see that this invariant, which is the most important invariant, which is p x y is an p, the top of the heap must be an optimal path, this invariant does hold, because we said that if it is not the top of the heap, then we must have missed generating the optimal path p star, but that can never happen during the course of the algorithm, and these things are just by the observation of the algorithm, right? So I will just take a few minutes and complete the analysis, it doesn't take too long. Yeah, so okay, so we want to do a running time analysis of this algorithm, right? And we want to argue that it actually takes what we claimed. So I'll quickly go over the initialization, and the initialization is fairly simple because we are simply going over the pairs xy and doing some heap operations. So the heap operations are always going to take order log n time, and there are n squared initializations we do for every pair xy, and that takes order n squared log n time. So the initialization takes order n squared log n. what does this remove top path from the heap correspond to in terms of the heap operations? It is an extract min, and for how long will you keep extracting? As long as the heap is not empty, but for every pair you just have one estimate into the heap. So you cannot do more than n squared extractions. So this loop runs for n squared time, and therefore there are at most n squared extractions from the heap. In fact, you may stop earlier when you start seeing infinity, because there can be nothing larger than nothing better to take out. So therefore this is taken care of, right? So now what we have actually claimed is that this thing, that whenever uv comes at the top of the heap, it must be an optimal edge. That is what we said, it is an optimal path. Therefore this edge does belong to E, this belongs to that E star, and therefore we said that M star is the number of optimal edges. So therefore if it is an optimal edge, each of these updates to W can be charged to the optimal edge, right? So you take every optimal edge and think about it being given some amount of charge. What is that charge? It is the charge that can be used to pay when that edge gets extracted and it does some processing, right? So when that edge gets extracted as an optimal edge, you are going to pay that charge, but how much do you pay? This is for every W. This can be order n. So we have spent, if we give an order n charge to every optimal edge, it suffices for that. Therefore this amounts to total of m star n. This operation throughout the course of the algorithm doesn't charge us more, or doesn't take more time than order m star n, right? The last is the one which is important, which says that you look at an edge which again is an optimal edge. So this third operation, which is of the form tu, and this can be invoked for several different things. That is, it could be invoked for tu y1, tu y2, and so on, right? And so therefore the same edge is being invoked or charged for several different vertices. But every time you invoke this must be a shortest path. That is why you must have invoked this. And so how many endpoints can be there for this? For these y1, y2? Again order n, actually n minus 2, because t and u are taken care of. So again you have at most n minus 2 endpoints here. Therefore again for the step 3, if you put a charge of order n on every optimal edge, for every step 3 operations the edge can pay from its own pocket for the step 3 operations, optimal edge can pay for those operations, and therefore all the operations other than that are something which are heap operations, which are taken care of by charging a log n for every such operation. So therefore all these step 3 operations taken together will again cost us m star n time, right? And therefore what we are saying is that each of these may actually trigger an update which we will multiply it by the log n, which is for the decrease key. So what we get is, this is an n squared log n here plus order m star n log n here for step 2 and step 3, which together gives us the bound that we claimed for, right? So which takes the whole thing, which runs in order n squared log n plus m star n log n.